When you try to learn quantum mechanics, you get bombarded with a lot of confusion. Particles behave like waves, and looking at things has weird consequences. So, if you feel like this, don't worry, it will be fine. You're not broken, explanations of quantum mechanics are. So let's fix it. Let's start learning quantum mechanics the right way. Hi, I'm a physicist, and here's how I would have liked my introduction to quantum mechanics. I'll clear up its two biggest misconceptions that leave you frustrated and keep you from actually understanding it. For some reason, both are usually not taught, but what is taught is confusion, historical confusion, that we just keep passing on. I give you an alternative, an intuitive introduction to quantum mechanics, and then its main features will just follow naturally. But this video is just the start. Over the next few weeks, I want to tackle our biggest questions. So, if you have any questions or thoughts, please drop them down in the comments, so we can figure out together what we're missing and clarify things once and for all. Alright, let's go. I think by far the biggest misconception about quantum mechanics is what quantum mechanics actually is. Because quantum mechanics is not a specific theory, but it is often taught as if it were one. Actually, classical physics is also not a specific theory, but most people have never heard of this as well. So, what actually is quantum mechanics? It's a framework, a toolbox, a set of rules telling us something about how things can move or interact, but nothing about what those things are. Okay, let me clarify this. Physics is about finding descriptions of the world, and we have basically two different toolboxes we can use to build such descriptions. One is the classical toolbox, and the other one is the quantum mechanical toolbox. You can now take the tools out of one toolbox to build a description of something. For example, you can use the classical toolbox to build a description about how planets move. But you can also use it to build a theory about electromagnetism or even general relativity. So, classical physics is not a specific theory about something, but rather a framework we can use to construct theories about things. In the same way, quantum mechanics is not a specific theory, but a framework within which we can construct a theory about something. Just like you can build classical electromagnetism, you can also build quantum electrodynamics. Two theories, both describing electricity and magnetism, but constructed with different tools. As a result, they give us different rules about how electricity and magnetism work. They are consistent with each other. But quantum electrodynamics is more precise and has a wider range of applicability, so it gives correct results in more cases. Why? Well, turns out that the quantum mechanical toolbox is better suited for describing tiny microscopic stuff like atoms or particles. But it's harder to handle, so the classical toolbox is therefore more useful for larger macroscopic stuff. So, instead of saying quantum mechanics and classical mechanics, it would be more helpful to call it something like microscopic or atomic mechanics and macroscopic mechanics. But we have those names due to historical reasons. So, that's what quantum mechanics actually is. A framework for doing fundamental physics. It can provide us with rules about how things move and interact, so we can use it to build theories. So, let's build a quantum mechanical theory about a coin to develop an intuition for quantum mechanics, and then we'll understand its key features. But first, I want to clarify some things about how quantum mechanics is usually introduced. Hopefully, this will show you that your confusion is really not your fault. The typical introduction to quantum mechanics. So, we now know that quantum mechanics is a toolbox. But you can't understand how a hammer works if you don't hammer a nail with it. That's why when we teach quantum mechanics, we usually apply it directly to particles like electrons or photons. But we forget to mention the hammer and nail thing. Instead, introductions often start with the double-slit experiment. Why? I guess to show how confused physicists were when they were still trying to figure stuff out. And to show how weird quantum mechanics is. Well, I mean, I get it. This is an historically important experiment, and maybe you should look at it someday. but not while you're completely confused because you don't yet have any clue about what's going on. Because this is just passing on more confusion, historical confusion, about whether electrons are particles or waves, which is not actually a question you should ask yourself. First, because in my personal opinion, it does not matter how you call them. Second, and more importantly, because this question is answered. What they actually are is vibrations of fields. If you want to know more about this, please tell me in the comments. But basically, at the deepest level, our world is made of fields. At least that's our current understanding. A field is something that fills all of space and has a specific value at every point in space. If all those points have the same value, the field is constant. But if it's not constant, if it starts vibrating, we can see those vibrations as particles like electrons. So there's an electron field, and if it's vibrating, we see an electron. This is nothing that comes out of quantum mechanics, because quantum mechanics is just a toolbox. Only if we apply this toolbox to fields, we get our fundamental theory of the stuff that makes up everything. The standard model of particle physics. It's a quantum mechanical theory of fields, a quantum field theory. We are still using words like particles or waves because it's more convenient than saying the vibration of the field or the energy moving through the field. I mean, we can just decide what we want to name it. We just need to keep in mind that thereby the word particle gets a different meaning than it usually has. It's not like a dust particle. But this is something physicists love doing, taking ordinary words and giving them a different meaning, simply because we need to use some words. But this can be pretty misleading, because often we're using those particular words due to historical reasons, and they don't quite fit anymore. Like the word quantum mechanics, for example, which I will explain another time. Well, and sometimes the words we use seem like regular words and you don't even notice that they have a different meaning. So, in general, when it comes to physics, if something is confusing you, remind yourself that you basically need a dictionary to understand it. And most times you did not get one. So, now that we've talked about how not to do it, let's turn to an intuitive introduction to quantum mechanics. Let's flip a coin. If we look at the coin, it's either heads up or tails up. Looking at the coin is a way of measuring it. So we can say our two possible measurement outcomes are heads up or tails up. Using our classical toolbox, we would say that heads up or tails up are not just the only possible measurement outcomes, but also the only two possible states. State is the word we use for the description of the current situation. So, it can be either heads up or tails up right now, and when we measure it, we know exactly which one it is. The current state is one of the two possible measurement outcomes. Knowing the current state, you can predict what state it will be in, thanks to the classical toolbox. This is nice. In classical physics, you can in principle measure anything you want to know, and then you can make predictions that are certain. This is something I explored in this video. So, if we have all the required information, we can calculate if the coin will be heads up or tails up. Now, using our quantum mechanical toolbox, looking at the coin, it's still either heads up or tails up. Those are still our possible measurement outcomes. But those are not our only possible states. A state must not be one of the possible measurement outcomes. It can be, but it can also be any mixture in between. So, the current state can be partially heads up and partially tails up. When the coin spins in the air and you look from above, there are moments when it's clearly heads. But there are also moments when it's just mostly heads, when the coin is slightly tilted. And when it's completely tilted and you see the edge, it's half heads, half tails. But it will land on one side or the other. From its position in the air, you can kinda guess what side it will most likely land on, but you cannot know for sure. So, in quantum mechanics, a possible state is not given by one possible measurement outcome, but by a combination of all possible measurement outcomes. Thereby, each measurement outcome is weighted. Those weights are numbers that tell us how likely it is that we will measure this specific outcome. So here, this number should be higher than this because it's more likely to land heads up. Here it is equally likely to land heads up or tails up, so the numbers are the same. The probabilities are 50-50. Now you could assume that the numbers are therefore 0.5 because of 50%. Well, kinda. They are the square root of 0.5. So, if we square the weight of a possible measurement outcome, we get the probability that we will measure this outcome. And the sum of all probabilities adds up to 1. Importantly, the state that describes the situation is a mixture of all possible measurement outcomes. By the way, you may hear the word state vector or wave function. Those are basically what I just called state. And if you hear the word superposition, that's how we call this mixture. This mixture thing has huge consequences. Let's say the coin is more heads up. It is nevertheless still possible that it will be tails up when we look at it. We cannot make a certain prediction about what side will be up. We can only say it is more likely going to be heads up. In classical physics, we were able to precisely predict a future state, if we had all the required information. But in quantum mechanics, we can't do that. We can only calculate probabilities of measurement outcomes. But those probabilities are not like the probabilities we are used to, which brings us to the key features of quantum mechanics. In quantum mechanics, we can only calculate the probability that the coin will be heads up, but this is not due to lack of information, as it would be in classical physics. Tossing a coin is, of course, actually a classical process. I just used it as a metaphor, because I think it's kind of an intuitive approach. But in classical physics, if you knew exactly how the coin got tossed, at what angle and with what power, you could calculate how it lands. But this is extremely difficult to measure, and also you would need to know everything really precisely. So if we cannot predict the outcome, that's because we lack information or skill. But with perfect knowledge and sufficient computing power, we could in principle calculate the outcome precisely. This is not how probabilities in quantum mechanics work. In quantum mechanics, probabilities don't originate from a lack of information or skill. Actually, they don't originate from anything. They are just there. In quantum mechanics, probabilities are fundamental. The fact that we can only calculate the probability of a certain outcome is a fundamental feature of quantum mechanics. A fundamental feature of YouTube is that it depends on your support. So if you like this video, please leave me a like. Thanks. The same applies to the fact that we can't measure anything we want as precisely as we want. You can either measure the position of a particle or its velocity, but you can't precisely measure both at the same time. This is Heisenberg's uncertainty principle. This is not due to lack of information or skill. This is a fundamental property of quantum mechanics. This is one of the key features of quantum mechanics. It is fundamental that we can only predict probabilities and cannot measure everything simultaneously. This is pretty confusing. It is so counterintuitive. And I will come back to this. But first, the other key feature of quantum mechanics, which is actually even more confusing. Luckily, we already met a version of it. As long as our quantum mechanical coin is in the air, it is a mixture of heads up and tails up. It's in a superposition of heads up and tails up. But as soon as it lands and we look at it, it is either heads up or tails up and nothing in between. Carroll puts it like this. What we see when we look at the world is quite different from how we describe the world when we're not looking at it. So, we believe that things are different when we are not looking compared to when we actually look. That's what they mean when they say the wave function collapses. The wave function, the state, the description of the situation is a mixture of all possible outcomes. But as soon as we look at it, we see only one specific outcome. From a mix of all options, we end up with one. And I guess that's why they call it collapse. But this is just a word, and as I said, physicists are really not good with words. So don't wrap your head around it. The meaning, this here, that's the important bit. What we see when we look at the world is quite different from how we describe the world when we're not looking at it. That's already confusing enough, which brings us to the second biggest misunderstanding about quantum mechanics. Now you might say, okay, these are the key features of quantum mechanics, but I still don't understand why that's the case. I don't understand what looking at it is even supposed to mean. I think that's the second biggest misunderstanding. Thinking that you should have answers to these questions. Because there are no answers. Okay, first, you cannot understand why it is like this. because we don't know why it works like this. We just know that it works like this. Physics only really answers how things happen, not why they happen. The best answer physics can give to a why question is always because the laws of physics tell us so. If I ask you why apples fall down, you probably say something like because of gravity, or because the mass of the Earth pulls on the mass of the apple, or because space-time is curved. But these are basically just different ways of saying that it happens because that's what the laws of physics tell us. The job of physics is to tell us how something works, and not why it works like this. In classical physics, it feels just more intuitive. To make peace with this, I guess we just have to accept that it is like this, even if it's super weird and non-intuitive. And that it's okay to be confused. Also, because the answer to the question, what is looking at it even supposed to mean, is, I don't know, no one knows. I will talk about this more in an upcoming video, but in short, this is the so-called measurement problem of quantum mechanics. And it is not solved. So if this whole what counts as looking at it, what counts as observation, or when exactly does the wave function collapse thing confuses you, then you can just join the physicists, because this is something we don't know. If you now know more than before, please consider subscribing and hitting the bell, so you won't miss the other videos on quantum mechanics. Thanks for watching, have a wonderful day!